Yeah, thanks for coming this early to talk about JavaScript malware, especially after yesterday's gala. Really appreciate it. So yeah, this is defeating Node.js malware through API tracing or API tracing. And my name is Sven Rath. I'm a security researcher at Checkpoint Research, mostly researching crimeware or the cybercrime ecosystem. And I also blog at eversince.com about stuff like malware development, Windows kernel, and so on. And yeah, this is also my handle where you can reach me on X or Matrix if you want to reach out or have a talk. So what are we going to learn today? We're going to talk about tracing as an analysis method for reverse engineering. We're going to talk about Node.js malware, so a little Node.js malware 101. What is Node.js? What are pros and cons of using the platform for malware, and so on. And then we're going to apply tracing to Node.js, and we're going to talk about how Node.js can be traced. And finally, I'm going to showcase some use case examples for a tool I wrote, which is the Node.js Tracer. So some video demos so you can see it in action. So what is tracing? Generally, you can say tracing is like you're tracking the path of execution of a program through its different API calls. And usually that is implemented by hooking into these APIs or by some sort of instrumentation. And for us reverse engineers, this means it's another method of dynamic analysis, like debugging, for example. So you're focusing on behavior rather than static aspects of the binary, like disassembly, pseudo source code, or in this case of scripts, like source code analysis. Just to illustrate this, here's a fictitious tracer called Trace, tracing an example PE. And in this case, the tracer is instrumenting all the anti-APIs, so all the syscall wrappers. And just by running this example PE under this tracer, you can sort of immediately see what's going on in this binary without even looking at like a disassembly or something. So in this case, you see that binary is calling anti-create file, so it's opening a handle to a file or creating a file, writing to the file twice, and then closing the file. And now you can augment this, you can add more logging. You can, for example, start to log interesting parameters to these functions. And now we know even more. We can see it writes hello world, and then it writes bye world. And you can take this a step further, and you can start logging every parameter, but you will see this already exceeds like the size of the screen, so it's sort of the balance to have when tracing, like how much do you want to log, how much do you want to omit, and have to find like a meaningful balance between the two. So why would you use a tracer? I personally use tracers whenever I encounter stuff that is like heavily obfuscated, because tracers just cut very well for obfuscation, like even if it's, for example, a virtual machine-based obfuscation, at least to a certain degree. Because if you like think about it, even a virtual machine obfuscated binary or script still has to call out to APIs when it's trying to interact with the outside world, with other processes or memory and so on. So by just tracing these calls, you can sort of infer what is happening inside that obfuscated binary script or whatever. And another good thing about tracers is they do not really require any interaction. You just literally run the program, or even like prior knowledge about the program. So if you're debugging, of course, you sort of need to know, okay, what could this binary be doing? What could the script be doing to be able to set like the correct breakpoints and so on. But for tracing, it's literally just run and that's it. So it's very low effort in both time and brain power. And that means it's very good for triaging and also in combination with static analysis. And I will show that later on in the video demo. And also I said already tracing is based on hooking. And since we are hooking all these APIs, it means we can also spoof these APIs. And this means we can defeat anti-analysis. And I will go into detail a bit later. But for example, if you have like these these debugger detection APIs, like is debugger present W or something, if you're already hooking into these APIs, you can spoof the return values and then pretend to the malware that you're not debugging it or not analyzing the malware. And finally, for the modern times, the trace log is much easier to analyze by an LLM than if you directly feed it an obfuscated script or binary. And I will also showcase that later on. Of course, there's also some constraints to using tracers, which would be that you don't have visibility beyond the API calls. So yes, you see what is executed, but you don't see the unexplored code paths, you don't see the logic, like the comparisons, calculations, if and else branches, and so on. You just see what did the binary execute, and this is enough a lot of the times to figure out what it is doing, but of course it's not a fully detailed analysis. And so tracing alone won't help you in like something like source code recovery. So if you're interested in analyzing a malware and really getting detailed into it, tracing alone won't cut it. Here are just some tracers that I use. So for PEs, I use API Monitor. I would call it a tracer. I've been using it forever. And then also Tiny Tracer by my colleague Casherazade. It's based on Intel pin technology. It's a very great tracer for PEs. It's not really tiny anymore. It has a lot of features. And then for .NET, Windows drivers and Node.js, I wrote my own tools. So that's Netrunner for .NET. Driver trace for Windows drivers, which is cool for all these like VM protected rootkit or cheat drivers if you're analyzing those. And then finally for Node.js, what this talk is about, I wrote the Node.js Tracer, which you can find on the Checkpoint GitHub. For Unix, there's also the strace utility, which is, I think, installed by default on most distributions. And actually, x64dbg also has a tracer, which is natively integrated in the debugger. I don't really use it much, but I think it's very useful if you do use it. And there's many more, but those are just the ones that I use. Okay, so much about tracing. Now let's get into Node.js. So what is Node.js? Node.js is essentially just a JavaScript runtime which is built on the V8 engine of the Chrome browser. So they took the JavaScript engine of the browser and made it essentially a standalone utility. So this enables you to execute JavaScript outside of a browser process. So sort of like Microsoft's JScript engine. Maybe you know if you double-click a JS file on Windows, it runs it by default with the JScript engine. And Node.js is sort of similar to that. And why do threat actors choose Node.js? Well, I don't know, but I think it's for these reasons. It's very easy to obfuscate. You just copy-paste the script into some sort of obfuscator, which are usually just websites or something. It's very easy to write, although in the age of LLMs, I would argue that most malware is easy to write in any language. And the probably most important point is that many AVs, antiviruses, have issues with static detection of Node.js if it's obfuscated. And I will show you why in a second as well. And it is, in fact, very hard to deobfuscate. There's mostly no like automatic deobfuscators, so you would have to like do some AST parsing and so on. It's very tedious work and often not really fun. Yeah, also some caveats. Node.js malware ends up being rather large in size, so it can exceed like 40 megabytes, because you usually need to pack the malware into some sort of, or pack it with some sort of node interpreter, because you want it to run it, or you want it to be able to run even if the victim doesn't have Node installed. And that's why you will find it in, commonly in like pretexts like cracked software or malvertising, like all these classic cybercrime vectors, because there the victim is already expecting a sort of big binary, like an installer, for example. And also, and this is in my opinion the biggest caveat, the OS interaction is very limited. So you cannot like directly call Windows APIs or something like that, but you are sort of restricted to what the Node API, which is the API that Node.js exposes, gives you in functionality. And this is why you will often see that malware will finally resort to like shell execution, like we'll call PowerShell or some other process, or it will just drop and run the next stage. So you will see Node.js a lot in stuff like loaders. I just collected some more trivia because I think Node.js is a really interesting platform and has a lot more to offer, which you sometimes don't even really see being used that much. But I will not go into detail, I'll just briefly mention it here. And the first thing would be Node add-ons. So Node add-ons are essentially just DLLs that you can call from Node.js, which have a certain export. And they sort of solve this problem of the limited Node API. So you can write native code and call that from Node.js. Then there's also V8 bytecode, which is essentially just compiled JavaScript, compiled into bytecode. And this can then be invoked from a Node script. And we at Checkpoint, we developed a decompiler for this V8 bytecode called Vue8, so we got you covered there as well under that link here on GitHub. Another interesting technique is electron backdooring or electron hijacking, depending on how you want to call it. This is essentially some sort of persistence method. So you know, Electron, stuff like Teams, Discord, all these Electron apps, they are essentially just having the JavaScript files on disk, and you can just, if they do not enforce integrity checks, you can essentially just backdoor these JavaScript files, and then the code will run anytime that app is started. And then there's red team frameworks like Loki from IBM X-Force, which I haven't seen yet used by actual, like in the wild threat actors, but I know that red teams use them. And really briefly, these are C2 frameworks, which are essentially based on this idea of hijacking Electron apps, but they reuse Node add-ons from other, like signed add-ons from other applications for execution. So you can think about it as bring your own Node add-on, if you want to call it that. Yeah, so this is just some stuff which I find interesting, but it's not really relevant for the talk. So what does a typical Node.js malware look like that you will encounter in the wild? And with that, I welcome you to my How to Become a Crimeware Developer crash course. And it's very easy. So you start with something like some anti-analysis checks, right? You don't want to run in a sandbox. You don't want to run, your binary doesn't want to run if it's being analyzed. So you do some checks, like for example, checking the total memory, like the RAM, checking the amount of CPUs. And if it looks like some sort of VM, then you prank the researcher by doing something benign and exit the process. Now afterwards, of course, you want to run as administrator because you want to steal all the juicy stuff. And as I said, the Node API is very limited, and there's no run self-as administrator API or something like that. So in this case, you would need to resort to calling PowerShell to restart yourself as with administrative privileges. And now you are running as admin, you are not in an analysis environment, so you can fetch your next stage from some sort of C2, write it to a temp folder or whatever, and execute it. And now you take this little script, your little stage 0 Node.js malware, and you put it in some sort of obfuscator. And as I said, it's very easy to do. You just go to something like obfuscator.io, which is literally just a website, copy-paste your script, and then it looks like this. So just an atrocious blob of obfuscated JavaScript. And this is what I said earlier, why it's so hard for static AV engines to detect if something is malicious, right? Because how can you differentiate this from some sort of benign but obfuscated JavaScript? So yeah, I guess that's the reason why Node.js can fly under the radar of AV so good. And then last thing you need to do is essentially just pack it in some sort of packer, so Electron or Nexi, so you get a PE which is ready to execute and does not depend on the Node.js being installed on the victim. And boom, now you get certified crimeware, and you can write very generic Node.js malware. And I would say this is probably what like 80 or 90% of Node.js malware that I personally find in the wild looks like. And I was looking at exactly something like this. In fact, this was actually the obfuscated source code of the binary I looked at, or the malware I looked at. And I was looking at this malware, and I really didn't feel like deobfuscating it because I just wanted to see what does it do, does it drop a next stage. I don't want to spend like 2 days doing this. So I asked myself, can I maybe hook into Node.js? Because that's what I do with other stuff as well. If I want to triage, I just trace it really quick. And it turns out that hooking is actually very trivial. So you see it on the right here. You can just save some function, like in this case the filesystem.open function, and then you replace that function object by another function where you can then log the call or the arguments, spoof or whatever you want to do, and then call the original you just saved. So this is like classic hooking, but in a script language. Now I asked myself, okay, I don't want to do this one by one for every API that might be interesting, so how can I hook into all APIs? And my solution was that I just hooked the load API, which is essentially just the Node internal API that is called whenever a module is loaded. So whenever a module is loaded, load is called, and in this case, I would load the module, and then I would iterate programmatically over all the functions of that module and hook them one by one. Yeah, so now I got all the APIs hooked, and then I realized, okay, if we can hook, we can also spoof. So I started like defeating the anti-analysis checks one by one. So there was this OS total memory function, which I showed you earlier. I just replaced it with like a lambda function, which always returns 16 gigabyte. So now whenever the malware checks how much RAM I have, it's just 16 gigabytes, so it looks legit. Same for the CPUs. I just return 4 i7 cores, looks also legit. Anti-analysis bypassed. And then for all the execution-based stuff, like I said earlier, you need to, if you want to go beyond the Node API, you will need to execute other stuff. I just also did it one by one. So for example, task list is something that is often called by these malwares to check, like, is Wireshark running, is IDA running, are any analysis tools running? And I just return an empty list if that is called, and yeah, that defeats it. And funnily enough, I could defeat like almost any PowerShell-based check with just returning 40,000, which is really stupid. But so for example, one was checking the amount of ports, like physical ports that a machine has. So it just checks, is this more than 0? And 40,000 is more than 0. Or another one was using WMI to get the video controller and then checking it against the blacklist, like is this VMware VGA, and 40,000 does not contain VMware, so that works as well. It's very stupid, but it worked against essentially all of them. And then on the bottom, there's another edge case. The point is, you can just build your library of anti-analysis stuff, and it will grow with every malware you will encounter, and yeah, it will just make your life easier. So last question was, how do I inject my hooks? And luckily, that's also very easy in Node.js, because Node.js has this feature called preload, and that's just a flag, --require, where you can set a script which is loaded before everything else. So you run before the malware, we can hook into everything, and then the malware script is run. And the great thing is you can also set this via an environment variable. So by setting this node options variable, this is respected by all the packers. So like Electron, Nexi, they all respect this, this variable. So you don't even need to unpack those. You can just set the variable, run the pack PE, and the tracer will be injected. And finally, I just added some quality of life features like skipping sleep. If the malware sleeps for like 2 hours, it's just skipped. Saving written files. If the malware maybe deletes a file after downloading, it's just copied to the directory. Displaying stack traces, which is very helpful if you combine it with static analysis, which I will also show, and logging HTTP requests and so on. And these are just like configuration variables that you set in the tracer, like you can see on the right. So yeah, let's see it in action. This first video I have is for the GachiLoader malware, which is the malware I was showing earlier in the cybercrime crash course. And let's see if this is visible. Yeah, looks good. So here you can essentially just see, is it visible? Like, is it big enough? Yeah, okay. So I'm just running the malware with like the tracer. And you can see after like a few seconds, it's essentially done. And you see all the API calls that this malware has done. And now, just from looking at this trace, we can really easily figure out what it's doing. So it starts with like all these require calls. So on the left, you have the call of the name of the API, and on the right, the info. All these require calls are just the modules that are loaded. So it loads the HTTP and HTTPS, so it does some C2 action. It loads the child process, so it will probably spawn a child process, and so on. Then we see it resolves some sort of temporary path, which is actually for the mutex file used later on. And then we see all the anti-analysis. So here it calls total memory, which we spoofed. So it proceeds. Then it called the CPUs from the OS module, which we spoofed again, so it proceeds. Then it also checks like the username and hostname against some sort of blacklist of common sandbox usernames and so on. Then we have task list, again spoofed, and all the PowerShell-based anti-analysis, which I talked about. And now this is the point where all the anti-analysis is done. Then it runs net session to check if it's running as admin, which it is. It continues. Then we see it creates this mutex file. And up next is some Windows Defender killing stuff. So it's killing the SecHealth UI process of Defender. And then it does some fingerprinting over PowerShell. So the PowerShell command is visible here from the exec sync API call. And here we have the first C2 hostname. So it sends all these fingerprinting information as a post request to this path. And then finally, it gets the next stage from another C2, and that's also logged in this request.txt file. And we can see the host name, the port, or the IP in this case, the path, and, which is interesting, some headers. As you can see here, it has custom headers, and it has this X secret Gachi family header, which is sort of an authentication token. So without this secret header, it would not return the next stage, but with this header, it does return the next stage. In this case, my VM doesn't have internet, so it stops at this point. But yeah, you can see, just by running this, we sort of immediately have an idea what it is doing, and yeah, didn't even have to look at the source code even once. And of course, this was also so easy because I sort of know what is Node.js Malware, how does it work, and so on. But for someone maybe not experienced with this stuff, this can be augmented using LLMs very well. And I said this earlier, if you feed an LLM a very obfuscated piece of JavaScript, it will most of the time have a hard time. It depends on like the pipeline, the model, and everything. Some models are really good, and if you give them like the tools to call, they can actually use all the AST parsing deobfuscated. But still, if you just feed a trace to an LLM, it works, in my experience, much, much better. And this opens up some sort of nice use cases. So if you think, for example, of like a SOC, and you are an analyst who is maybe not a reverse engineer, but just triaging tickets, and you get a ticket, okay, hey, we found this Node.js malware on this machine, can you check if it's malicious or not? And now imagine you have a pipeline where that malware is run automatically in some sort of container or VM. A trace is created, and then that trace is sent to an LLM. This LLM sort of gives you a triage, is this malicious or not? And this can be very powerful and yeah, time-saving in the end. So I'll show you how Claude is actually handling these traces. So I made it a very simple prompt here. So it says you're a Node.js malware analyst who is given the task to analyze this given malware trace, figure out what this program is doing, potential anti-analysis checks, mutexes, configurations, C2 server addresses, or relevant unpacking logic. Summarize your findings briefly in a markdown report. And then I just fed it the trace, like exactly the trace that I showed you earlier. And we will see this doesn't take too long. And Claude sort of figures out all the stuff that I just mentioned. So we see the overview. This is a Node.js-based info stealer dropper. It is a dropper, it's not an info stealer. But that is correct. And it also identifies all this reconnaissance and fingerprinting stuff. So all this PowerShell calls, the running processes, the CPU count, and so on. And it also identifies that these are VM or sandbox detection stuff. It sees the AV termination, the when defender service probe, the mutex and log file was correctly identified, and of course also the two C2 pairs, along with their ports and their roles, like one is the primary and one is the secondary C2. Yeah, at the bottom you also see like the two endpoints were correctly identified. One is for sending the fingerprint data, and one is for the next stage payload. And it also correctly identified, yes, the X secret header is essentially the sort of authentication token or campaign marker, and is used to identify as the malware. And then at the bottom, we just have the IOCs sort of neatly lined up in a little code block. Yeah, so in my opinion, very powerful way if you want a quick triage of a Node.js malware. And the last thing I want to show is the stack trace analysis. So this is goes a bit more into like actual reverse engineering. So if you want to use tracing as a tool in combination with your static analysis. And for this case, I just took the same script and I beautified it. I didn't deobfuscate it, I just beautified it so that it's not all on one line, but it just has line breaks whenever appropriate, because otherwise the stack trace wouldn't have a meaning because everything would be originating from line 1, right? So yeah, and then I just run the tracer with stack trace set to true, or display stack set to true, And in this case, I intentionally removed some anti-analysis spoofing. So you will see we run the same malware. This time it shows the stack, the call stack for each of the API calls. And we see, in this case, it did not reach out to the C2, but it reached out to whatsapp.com and api.github.com. So this is some benign stuff that is executed whenever the malware sees that it's running in an analysis environment. And now we can trace this back and we can see, okay, apparently it took a path which we don't want. So what was the last thing that was called before? And in this case, it was the OS CPU's API that was called. And we can look, okay, this is in line 6334 of the malware. So we can just go there. This is actually the tracer script, which is wrong. So we open the actual malware script, and we go to that line where our stack trace was pointing us. And if we scroll down, we will, of course, not see the actual API call because it's all obfuscated. But we see this try-catch block, and we can see, okay, this must be where this call originated. And we also see some comparison logic, which, if decoded, would probably resolve to like checking the amount of RAM or CPUs. But it's not really necessary to understand that, because what we want to do is we just want to patch it, right? We want to patch this anti-analysis check so it actually proceeds. And we can try to return true, return false, just figure out what is this thing expecting. Or in this case, we just patch a return inside there. And that, in this case, is enough to bypass this anti-analysis check. So we can run it again. And we'll see this time it actually calls out to the actual C2. Yeah, so this is just to show you that, yes, tracing can be used alone to triage a binary, but it can also be used as a tool in combination with static analysis to help you pinpoint something down and use that to patch or just to understand the binary more instead of to just rely on static analysis. Yeah, one last use case which I don't have a video for, but I think it was really useful in the case of this malware. I used the tracer also for essentially payload extraction. So I just set the save file writes to true, which means that every time a file is written to disk, it's also written to another directory, so I can collect it there. Because this malware was getting the next stage, running it immediately, and then immediately deleting it, so I couldn't like really catch it otherwise. And I had like 120 samples of that, and I just ran them all in parallel through the tracer. And like after 2 minutes, I had all the payloads saved to my directory. So that was also very useful, sort of like dynamic extraction of payloads. Yeah, so takeaways. Node.js malware can be very trivially obfuscated, but you cannot really hide the runtime behavior. And this is not only true for Node.js, this is true for everything that is obfuscated. And a tracer can help you very well in cutting through that obfuscation without even having to deal with deobfuscation. And if you're dealing with something like Node.js, which is mostly just a loader for a next stage, you're not really interested in getting all the details. So I think this is a very great use case for tracing. And spoofing, as you saw, is very powerful because we can bypass all these anti-analysis tricks by simply just spoofing return values. And finally, I would say tracing is a useful tool in the reverse engineer's toolkit, but you should use it like that. It's not a silver bullet. You shouldn't rely only on tracing, but it is a very useful tool. And if you use it in combination with debugging, with static analysis, with deobfuscation, you can get very far, and not only in Node.js, but in all sorts of malware. And last but not least, defeating the tracer is very easily possible. I know at least 2 ways. I'm not going to tell them, of course, because I haven't yet encountered them. But in theory, it's not that hard. Thank you very much. And if you want to try out the tracer, this QR code or link will take you there, and I'd appreciate any feedback, issues, contributions, whatever. Thank you.
We can take one question for Sven. There's more people than
here. I think you pretty well answered my question just in that very last comment, as in, do you see any unhooking going on? We do this with Windows APIs all the time, and of course, the malware when they realise that they might be traced.
Yeah.
So you've not actually seen that happen in the wild yet? Or?
I haven't seen it yet because this tool is not so known, so I don't think it's in the like threat model of these actors. Like they are not doing anti-tracing checks yet, but in theory it is of course not that hard, yes.
Yeah, and have you seen that kind of tracing used maliciously maybe? I mean, like malware putting itself into the environment variable for Node.js?
No, not yet, but it's an interesting idea, yeah.
Yeah.
I haven't seen it yet, yeah.
Thank you very much. Thank you, Sven.
Yeah, thank you.